All right, that's called the photoelectric effect, and we'll spend a little more time with that later. The next thing that was clearly an experiment, which clearly led to some great trepidation, involved something called the Michelson-Morley experiment. You remember, late 1800s, there was a problem with light. What was the problem with light? Light acted like a particle some days, sometimes it acted like a wave. Now, Einstein fixes that with the idea of a photon. It is a particle which is a wave inside, right? Or a wave broken into small particles. That solves that problem. So that's not the problem I'm talking about. What I'm talking about is when Michelson-Morley were trying to figure this out, they did an experiment which is indeed troubling. If you imagine the sun, this would be really better if it was really pretty looking sun, but it's not. There's the sun. Here's the Earth. The Earth this way. When the Earth's here, it's going this way. It's here, it's going this way. And when it's here, it's going this way. And so the Michelson-Morley experiment was simply, hey, we're fascinated by the idea that there's ether in space. So that was the idea that, if it's a wave, it has to have ether, and if it has to have ether, then that ether is what the light is shaking. And so they believed that, well, since we're traveling in the ether, we should the difference whether we travel this way or this way, right? So, as an example, if you're trying to do water waves, you're sitting out in a boat and you're waiting for the water waves. The fact the water waves move this way, as my boat moves, experience it differently, right? My boat's going this way rather than going this way, it would change how my boat feels it. And so they thought that this would be a way to detect what's well and good. They discovered that, in fact, light is independent of this effect. And so therefore, the idea that it has a media became problematic. Quietly in the background of the experiment, there was one other problem with this experiment, and that was this, that lowered the speed of light. And you're like, Mr. Resney, why is that be a problem? It makes no sense at all. Why would traveling the speed of light be a problem? Well, think about it this way. Let's say I am sitting, I can't get my pen back. My pen is gone. Okay. Let's say and I put Mr. Harrell on the top of the bus, and I ask him to throw a pitch this way, consistently 20 meters per second. So he throws one pitch 20 meters per second, then the bus starts moving, right? It starts going this way. So the bus is going 10 meters per second. I ask him to throw another pitch. It doesn't take much imagination to realize this pitch would be going 20 meters per second, and neglecting gravity, the fact it's full. And this one here would be going 30 meters per second. And so that's in fact true. Here's the problem. The sun is right here, and it's sending light to here. So it's traveling to us. Remember, we're actually traveling ellipse, not a perfect circle. So there'd be little deviations towards the inside. And those deviations should be detectable. The speed of light at some places should appear faster. Other places it should appear slower as it gets received by this device that splits out the light. In fact, they had to remove all that equipment to make sure to see what was going on. They discovered that if you treat it as if it was going at the speed of light, no matter which way the Earth was going, it's not a big deal. Everything works. But why? What that implies is when Mr. Harrell's sitting on top of a bus, as the bus is going this way at 10 meters per second, he throws a 20 meter per second pitch, it still comes off at 10 meters per second. That shouldn't be. Shouldn't be. Unless he's sliding on the roof backwards. As he throws it, he's attached to the roof. It should go the same speed. And along the same problem with the Michelson-Morley was an additional experiment involving X-ray crystallography. X-ray crystallography was a chemistry thing. Again, we're looking for experiments because everything that's worth discovering has already been discovered. We know that there's crystals, and so to discover the properties of crystals, they were shooting X-rays at these poor defenses. Now, X-rays are, so when they hit this thing, they move it. They also cause ripples in the whole entire thing, and these waves bouncing back off, you collect, and it's really super cool. You can tell the shape by how it reflects off these crystals. There's a very fundamentally awful problem, and that is these atoms are really small. They're getting hit by X-rays, which are relative. Means these things are moving. They knew it. They could measure how much they're moving by. What made no sense at all is when the crystal would bend in right like this, instead of its original position here, when it snapped back, if it released that energy back, it would shoot out light going the other way while moving this way at a quarter the speed of light or something. This light was only moving the speed of light. So it's the same problem. If you're sitting on a bus and you throw a ball off the front of the bus, it's as if the bus isn't moving, or as if you're throwing it weaker. How does light know it can't go faster? What's going on here? Okay? All right. Now, last but not least in my fun-filled festival of weird experiments that don't make sense, Becquerel, French dude, photographer, puts a rock shelf in his drawer. He puts a photographic plate over here and discovers of the rock. The rock happens to be uranium. That is disturbing to him, so he takes it around and talks to whoever he can. Eventually, somebody can actually solve the problem. That's her name, Curie. This woman starts studying these rocks. Specifically, discovers it's an element. Discovers the element of uranium that's important. Then discovers other elements that do the same thing. And these atoms are breaking apart and shooting out energy. And that energy comes mostly as rays that are actually very lethal, and they end up killing Marie Curie themselves. These rays are coming from an atom which has a nucleus, right? It breaks into two nucleuses, and then suddenly there's a whole bunch of energy. Why? Where's the energy coming from? We know energy is conserved. Does this have energy? It must. What is its energy called? So they came up with all sorts of magic words to describe it. At the end of the day, they didn't know the idea where they were, right? Something about this allowed it to break into two pieces and release a tremendous amount of energy. They understood, by the way, that it was breaking apart because it was unstable. It had more energy before than it had afterwards. But why? What was the energy type? Okay, it wasn't electricity and magnetism. It wasn't gravitational energy. Something else was afoot. Sorry, Maxwell, we're not done yet. Something is going on. So these are the experiments that basically usher us into the land of modern physics. Explaining these experiments and these results are what sends us down a rabbit hole for which we almost never get completely out of it. All right? Send questions if I haven't been clear enough on something. Send questions. And that's enough for today.